Yes, I do, Ewan. How about you? Thank you. Thanks, Ewan. Let me stop sharing a screen for a minute so that I can be on video first, and then I'm going to come back. Yeah. So let me get back there. I want to stop sharing. Okay. It's good to be back, at least there virtually. Let me thank the organizers for giving me this opportunity. In particular, accommodating my last minute change from in-person to virtual participation. And since I'm using iPad, I was told that I can either share screen or be on video. So I'm going to switch off the video now and get back to the talk soon, share the screen. And when the question time comes, I'll switch back here. Yeah, is that okay? I'm sorry for this inconvenience. So having iPad does help me to write something if appropriate. So let me stop sharing that, and then let me share the screen now. Okay, I'm going to be discussing somewhat in a broader terms what our plans are for future based on what we have been doing over the last few years. Do we need frequency domain multiple scattering at all? That's the biggest question, which is what I'm going to be focusing on later in this talk. It seems that for multiple scattering, time domain is necessary, according to at least somebody. So I'll come back to that. So this is a joint work with Frederick Lello for multiple scattering, so in time domain. And Victor Dominguez and I been developing frequency domain heterogeneous models. I'll talk a little bit about this and how it's going to be related to what we're going to do in future. Of course, you heard the brilliant talk by Stuart Hawkins. So he's crucial to this entire picture, both in frequency domain and in future time domain, to make this time domain multiple scattering with large number of particles feasible. Okay. So, of course, there are a few other authors there. When I quote certain papers, it'll be clear. But for now, let me start by saying that the main focus is on time domain scattering with multiple particles. This is our recent work, what you see it on the screen. Let me quickly play the video of that. So what are we interested in is that when an incident wave hits a multiple particle configuration in time domain, are we getting physically appropriate waves? And can we get the same with frequency domain at all? What type of geometries that we can handle? And are those sufficient to do this? And also, can we also allow for certain geometries that have been used as a benchmark? This is called NASA-Allman. And how are we going to do that? So the whole idea is to develop a scenario, how we have done this, and what our future plans are. Okay, so that's our focus of this talk. So let's set the scenario now. So you got a bunch of multiple particles. So ignore everything else. So let's set the notation clear. So omega is a bounded domain having multiple structures if the number n ops is bigger than 1. We will be splitting into either impenetrable or heterogeneous. I'll tell you the reason why we do that, and I'll justify how we can do this one. And omega complement denotes the exterior problem. And that's a free space region having taken care of heterogeneity in a completely different way. And the boundary data is induced based on the properties of the domain omega, the particles in omega, and the incident field. So that's where now slightly some distinction is needed between frequency domain and time domain problem. So I'm going to use that capital LU. Whenever I use capital LU, it is for a frequency domain problem. And INC for the incident wave, typically think of a plane wave. And we will be computing scattered field. If it's purely at exterior model. If it's interior model, we'll be computing capital U, which is a total field. So the total field in the exterior is given by sum of that. So either we are interested sometime in just scattered field, many times total field. So that's a scenario now. So in the time domain, the incident wave depends on time. Of course, think about more as a Gaussian pulse. And little u denotes the unknown wave field that we are interested in. As I started preparing and focusing on only time domain, the notation, everything was getting horrendous. I thought, let me switch a little bit now and ask some fundamental questions and give a broader picture as opposed to spending the rest of the 40 minutes just on this one particular algorithm. Okay, so that's a switching gear now. I'm going to ask the question, are established continuous equations sufficient? So being a computational mathematicians, we normally tend to take it for granted, the continuous equations, yeah, and proceed with the numerical methods. But it's been over the last decade, it's been clear that you just can't take this for granted. You need to also worry about continuous equation and develop algorithms accordingly, okay? So in particular, this has been bothering me for a while because we have done a lot of multiple scattering in frequency domain. Is it okay? Because my colleague Paul Martin wrote a fantastic book on multiple scattering in frequency domain. And I believe that that is sufficient for me to justify, but some other papers just mentioned that don't bother, but we'll come to that. So the fundamental equations remain the same, the PDE. It's just this, you have to do a variational formulation or reformulation, depending on whether you're talking about the interior problem or exterior problem, for this fundamental equation. So this is a time domain equation, basic wave equation. So essentially, C square, capital C square, is heterogeneous in general. And it's constant exterior to the multiple configuration, okay, heterogeneous configuration. So this is one of the things colleagues at the School of Mines, especially Center for Wave Phenomena, they always used to tell me that there is nothing like a constant coefficient wave equation. Don't even think about this. Of course, I used to tease them that, hey, you know what? There's nothing like solving a problem on a square or a cube. That's not enough. So you need to take care of unbounded domain as well. So this debate has been going on, and I want to kind of, over a period of time, see whether we can do everything. So that's a time domain, capital C square. And in the frequency domain, and you have this both interior and exterior problem. For the exterior field, the scattered field, you have the radiation condition. So in that sense, that it is a constant exterior. So we are interested in both. Of course, the key is to come back to this. And before that, let me ask the question, which has been bothering me for some time, but I'm getting closer to understanding some of those. So our established time domain or frequency domain model is sufficient or even appropriate? Of course, this question has been raised about a decade ago, thanks to the chair of the session in frequency domain, Evan Spence. The first talk in this workshop by Simon really recalled that. The term called sign definite and sign indefinite. So in particular, until about a decade ago, for the frequency domain problem, Helmholtz equation was wrongly categorized. In particular, I am interested in the heterogeneous Helmholtz equation in the interior, while Simon highlighted homogeneous Helmholtz equation in a bounded obstacle for his work with Evan Spence. So there is this question of whether established models are sufficient at all. Okay, do we need to believe in that? So there is a wrong categorization that's been corrected recently. And also there are several papers that question the idea of truncation of unbounded region, approximation of the radiation condition, or dodging heterogeneity. That may not be appropriate. That's question 2. And the third and the most important question for this workshop is, for multiple scattering, there are claims that justify very well. Frequency domain models are not sufficient if you are interested in simulating physically appropriate wave propagation model. So let me take the item 1 and 2. I'm going to go a little faster. I apologize for that, but that is not the main focus of this talk, but I just want to give you an idea. And when I come to the later part, you will see why I'm kind of going on to talk a bit about number 1 and 2. So based on the timing, I may rush a bit on number 1 and number 2. Yeah. Okay, so I'll come to number 3. I want to spend at least last sufficient amount of time for multiple scattering in time domain. So essentially what has happened is that this is the question without the term heterogeneous was asked by Evan Spence and Andrea Myla in their 2014 in the SIAM review paper, and they solved the problem for homogeneous. So the question I've been interested, I've consulted with Evan Spence for many years rather. So you start with this Helmholtz equation ellipsis domain, heterogeneous, that's important. So that's why I'm changing the notation now, omega tilde, just to show that, hey, you know what? We are slightly off from the previous notation. So the problem is unique solution. That's no issue at all. That's where the standard formulation comes in. A lot of work has been there. There is something else is going on for the unique solution. There is this extra properties for the continuous model. This hasn't been exploited for the heterogeneous model for a while. That's why wrong term was done. So there is this catch here for Strauss-shaped and non-trapping. So you heard this term again and again if you attended Evan Spencer's talk. There are too many of those. I mean, he would use it often. And Simon also mentioned that So that's essentially for analysis purposes. In fact, we are interested in full analysis as well as very high performance computing implementation. So only for that. So I'm going to claim that maybe we won't need it. If you are a purely a computational person, don't worry about analysis. Okay. So where does this term sign indefinite come from? Because everyone uses this standard variational formulation in this space. And because of this non-coercivity, one calls it, the Helmholtz equation was termed sign indefinite. Nothing wrong with that. In fact, it's one of the best formulations. I've used it a lot. I will be using it, okay? Just because I'm going to put up with something newer doesn't mean that that's going to be end of the previous one. But the main questions are, is there a sign definite? Is there a of the form this in a slightly different space? And can we prove it? It is sign definite. Can we develop associated Galerkin method? And also, can we make it practical? Because over the last 5 decades, it is all about pollution error, higher order methods. Pollution error cannot be avoided almost in all cases. So you need a preconditioner, and a lot of things went on. So in that sense, that if you're proposing a new method, you need a good preconditioner. And so the question is now, can we develop a preconditioner for this? And then the further question is, does this preconditioner work for non-star shaped and shopping domains without analysis? Okay, so there'll always be Evan's friends around and other smart folks around to be able to show when it might work. Okay, so that's the idea. So why coercivity? Quickly, you got a lot of this goodies, yeah. That's important. Most importantly, the analysis of finite element method and also the continuous problem becomes easier. Simon mentioned that in his first talk for his rough surface scattering problem. He also highlighted certain open problem that's been sort of embarrassing for Galerkin method. So Galerkin method, once you have a sort of coercivity, it's pretty much clear that and then the CS lemma is available, and that's what it is, okay? So now that you have this, so there is some reason to say, do we have it? And what we answered for all the questions were, yes, it can be done. And I'm not going to go through the details at all, because that's not the focus of this talk. And because of doing all the answers to everything, not just the continuous formulation, then finite element method, and then preconditioners, comparison with the standard methods, and also doing all sorts of things. I mean, it's about 50 plus pages, and then to reduce to just below 50 to make it work. Essentially, we proved that the coercivity constant is uniformly in K. I prefer to use the term Ka or Kl. That is more appropriate, not assuming L is equal to 1. And the continuity constant is of order KL, which is what leading to pollution error. And also we developed for this coercive model associated preconditioned finite element method using shifted Laplacian. And why we need it, that's my question, right? So sometimes we may need this. One of the first outcome of this coercive formulation was there is this uncertainty quantification because we don't know refractive index precisely. And a lot of work has been done for coercive models, such as diffusion problems. It's been always a stumbling block to do the similar thing for wave propagation. And that was the first thing, outcome of this, this coercive formulation. Of course, it can also be done without coercive formulation, as Evan Spenders and his collaborators have shown. But the analysis is somewhat are relatable. The reason I think now such continuous model focus is important because numerical methods come and go, finite element methods and this and that, but finite element methods being standard, we took it for granted. But what I've been observing, at least having been in so many PhD committees by geophysicists, everybody's moving to so-called machine learning and neural network approximation. So physics-informed neural network approximation. So sometimes having such properties might help, but as of now, let's kind of keep it like that. So that's the idea. So essentially we implemented that, and then we can show if the solution is smooth, you can get a very high order convergence. Even if the solution is not smooth, still the higher order finite element does help. Again, I apologize for rushing this because this is not a main focus of my talk. And the key I want to mention is you can develop preconditioners without too much of expense so that you can have GMRS-based iterations uniformly in K. Yeah, that is one key development that's been going on for a couple of decades. So another advantage is that you can really develop methods for very large wave number problems without any fancy approximations, if you take into account a parallel high performance computing and a few other details. Yep. So bottom line is that we did develop preconditioner because you see now without preconditioner, this is ridiculously impossible to do this. So you can actually get wave number independent number of iterations for solving the linear system associated with that sign definite problem as well. So let me again emphasize, just because we have coercivity, it doesn't solve the fundamental problem of pollution error. And the pollution error does require preconditioning, and developing the right kind of precondition is important. In particular, that multigrid and so on. We did multigrid a while ago. My favorite and the main thing analyzed by Ewan and friends is that domain decomposition-based preconditioners. Okay, that's what it is. So just to finally give me one more minute, you can actually, the whole code actually works for non-star-shaped geometry as well. So it doesn't have to be star-shaped. And we are getting exactly the same result. Okay, so I've taken about 20 minutes of this already. So that's, as I see, if you found me rushing, so just to give you a focus that you need to sometime ask for a fundamental question, which is what I'm going to do for time domain scattering as well. Again, all these preconditioners work for non-star shaped as well. And who is going to prove it? That's another question. I'm hoping Ewan will do it. The second question we asked was, which is very crucial, by the way, because we are developing time domain algorithm with certain conditions. And I'm going to justify why such conditions are fine through this. So if we are interested in heterogeneous model and also accommodate homogeneity in the exterior. So we don't want to do any truncation at all. Okay, so that's our key requirement. You do this one, you do that, and also retain the heterogeneity. So there is, if folks know, there's something called splitting FEM and BEM. And we again focused on the continuous model. And we did something that suits us better. What is it? So as you all may know that for finite element methods, this sort of a domain is very, very convenient. However, for the finite element method, this sort of a curvilinear based finite element method is not very convenient to do this. So what we have done was for us, for the exterior problem, this is extremely important. For finite elements, for that's important. So what we have done was that we have developed overlapping decomposition with full analysis for the continuous model. And some of you already know that. The key to this whole game is to split the problem into two parts and able to join it. This is where the reason why I'm going to talk a little bit about it. For this full heterogeneous and homogeneous model, we are free to choose the interior boundary you see, which is smooth. That's what we are choosing. In particular, we can choose with spherical coordinate global parameterization. So henceforth, when I say domain omega anything and higher order implementation, please be aware that I am using this. Without that, it's very hard to come up with something what we asked. So this is what Stuart also answered when tough questions were asked. The spectral approximation is the key to the whole game. Yep. Of course, we talked about this polyhedral and polyhedral boundaries for finite element methods. Perfect. We can do higher order finite element methods. And this is the overlapping region. And that's why we call this. So the key is that such methods, related methods have been proposed. This we did it differently, somewhat differently. And we did a full analysis in both 2 and 3 dimensions, and also develop numerical methods on that. So that's what it is. So this is a split. You can take the full problem, split into 2 distinct problems. So this is what folks are familiar with, homogeneous exterior problem. This is the favorite of a lot of physicists and engineers and so on and so forth, heterogeneous bounded domain model. So that's what we talked about before, right? And this many talked about it. I'm going to talk about time domain scattering at this level. So that's what it is. You do this, and of course, you introduce 2 artificial boundary conditions, boundaries, but these are not physical at all. So unlike the standard truncation, we are not truncating anything at all. So we need to kind of find a boundary condition for these 2. So there's the whole idea that the solutions from interior solved in this rectangle you see and the exterior solve you get should match in this domain, in the overlapping domain. But actually, it is sufficient to match it on these 2 boundaries. That makes life easier. So essentially, you can actually solve this problem with unknown boundaries. That's what it is. So that leads to this sort of a domain decomposition type approach. So you solve the interior problem. That's what we initially talked about it. You solve the exterior problem. A lot of folks have talked about it. And then you need the input for this. So you eventually solve this problem after solving the interface. That's a small system, and it's a well-conditioned system. And then finally construct your exact solution. So this is capital U, should be. And we have done this work. So just to kind of ensure that we can solve heterogeneous and homogeneous problem with, for the exterior problem, the boundary of our choice. So the first one was essentially continuous model with some amount of computation. The second paper is on 2D full analysis based approach with a good amount of applications, and that's done. Okay, so these 2 questions are answered. So it's good to ask this fundamental thing. And the second part I introduce is to ensure that we are keen on smooth boundaries, which is not a favorite thing for standard method of moments-based boundary element methods, which can be done for any geometry. So in our case, we have some special requirement. So we did this part. It's called Janus particle configuration is one of the bigger things. And folks assume simple condition. In fact, we can allow general heterogeneity and unboundedness. And the key I want to point out is that this unboundedness is crucial for far field. And far field is fundamental for many, many applications. So that's why it's important to take into account of heterogeneity and also able to do unbounded problem. Again, I apologize for rushing through this because that's not the focus. So I want to kind of reserve some time for time domain model. And you will see as I introduce it, there'll be a lot of notation that goes on, and I could have done the whole lot. Instead, I'm going to ask the question that for multiple scattering, is it sufficient to do a frequency domain? Or is it necessary to do this? So, as I said, Paul Martin, fantastic book. I mean, I've been with him since 2003. It's for a frequency domain model. The key is that he himself mentions that multiple scattering may mean different things to different scientists. So for applied mathematician, it could mean something different. For an engineer, for a physicist, it could mean something completely different. But what about us as a computational scattering folks? We have to be faithful to complete mathematical community and also pure math and analysis. And at the same time, we keep claiming that, hey, we are doing real applied problems. The code can be used at the industry level and so on. So may mean different things, resulted in this in some sense. The paper by Locke and Mischenko, it's a very, very nice paper to read it. It just say, hey, you know what? Multiple scattering is purely mathematical construct in frequency domain. So much it goes on to explain that, hey, it doesn't even produce physically appropriate waves because of various missing parts, which I'm going to highlight at this. However, multiple scattering becomes a definite physical phenomenon when the interactions happen, appropriate localized pulse happen that way. So do we worry about late Mischenko's climb, or we should not, because there's a lot of work done for frequency domain. So what I'm going to argue is that for developing a real time domain multiple scattering, especially in 3 dimensions, you need, at least from a computational scattering point of view, you need frequency domain multiple scattering innovation. So is it going to be time domain or frequency domain? Well, a lot of people spend a lot of time on this. Stuart gave a very nice talk. He also pointed out about some of our work. So a lot of work went on. In fact, I wasn't even thought the Mischenko's work was done similar to the time we produced this. And then we've been doing that a lot. And so this is a frequency domain simulation done by Stuart. So the question is, it's fantastic. I mean, it looks great. We just prove accuracy. It looks physically, I mean, computationally fine, mathematically fine, looks good. So some may claim that it's a frequency domain problem. These are purely mathematical. You started with a mathematical problem. You did that. You got this, looks good. But as Mischenko's paper highlighted, that it may not be physically appropriate. So that resulted in some sense, I mean, that's one of the motivations for me to always look into time domain models. So we have done this work. This took quite a number of some years. So it's going to appear. Let me talk a bit more about this. The point I want to kind of emphasize is that frequency domain algorithms are important. Okay, so that's the model. So again, I'm going to rush, but the key is that we are going to use both Dirichlet condition, Neumann condition, and impedance condition. So most folks focus on Dirichlet condition. So this is that. So as you can see in a minute, the notations are going to be a bit more tricky. So we're going to use, because exterior problem, we're going to use a reformulation using time domain surface integral equation using this potentials. So this facilitates us to solve for only densities, either using a single layer potential ansatz or a double layer potential ansatz. And depending on the boundary conditions, you got to deal with lots of operators. So there's a single layer operator, single layer, double layer, adjoint double layer, and the hypersingular operator. The key is that if you have n obstacles, so you have order n square operator. So this is kind of gives you some idea of the struggle that Stuart highlighted. And then comes the actual problem that we are solving for the density. And depending on the boundary conditions, you have only the single layer operator, which is weakly singular, or you have only second kind equation, double layer operator, or both in terms of conditions. These are weakly singular, but you also need hypersingular operator in certain formulation, first kind, which is favored of many. And in particular, if you do a Neumann equation, we use hypersingular operators. So the whole idea is why we need frequency domain surface integral operators. Well, let me introduce this because one of the most favorite methods, at least to me, at least very good, but it's got a lot of disadvantage in terms of memory, is the Laplace transform based approach using convolution quadratures. And that leads to the Laplace transformed version of that. And you're back to your favorite kernel, frequency domain. And that's what the development has been. So you need to know how to discretize this operator efficiently, higher order algorithms, and so on. So that cannot be ignored if you want to solve this time domain multiple scattering problem using convolution quadrature based approach, or even other types of approaches as well. So just to quickly go through this scenario now, the Runge-Kutta convolution quadratures allow for transformation into frequency domain surface integral operators. What we use is the astable M-stage Radau 2A method, which is one implicit but very stable method. And also got to reformulate everything. If you're into this business, it's kind of quite get messy. You'll get into some kind of a low triangular Topliss structure, but then simple recursion relation kills you also in terms of storage. So the idea would be to use some kind of a fast algorithm and then use the memory reduction using some kind of a diagonalization process. So it kind of goes on and on. And at the end of the day, you do all of those things, you get the memory reduction. So this can be done also with the standard method of moments-based boundary element algorithms. Okay, that's been done in some form. But what you need is that for 3D problems, so 2D, it's okay. For 3D problems, in order to discretize various operators, to reduce the storage, you need a very higher order discretization. And that's where we come into picture using spectral Galerkin algorithms. So that's our contribution. So that made us to come up with this approach. And just give me just a minute or two to finish it off. So we've done a wide variety of benchmark comparison with the existing literature, and show that how do we gain in terms of frequency, in terms of memory, as well as in terms of CPU time. And that gain allows us to be ambitious about solving time domain multiple scattering problems. So this is a toy example so that you have exact solution, and then you can do a long time simulation. And that's possible, and it can be done quickly. That's not a big deal. The memory is not a big issue. But then when you have this benchmark comparison where you need for wideband signals, this is one thing one needs to do it to be able to be competitive. It's a very, very high memory requirement problem for this sort of a Gaussian pulse incidence. And we did gain something in terms of both CPU time and memory. And just a quick idea. So you can actually, instead of 54 GB, we could get into about 24, 21 GB problem. And that's done for sphere. That's what everybody does for the benchmark initially. Of course, we could do it for all other non-smooth obstacles. And also, lack of time, there is a fantastic algorithm by Alex Greengard and Alex Barnett and Greengard and Tom. So they also provided a very good higher order algorithm. So we also compared with that, and we got some kind of similar advantage in terms of memory and that. But again, caveat, we have our special requirement for the kind of boundaries we allow. So essentially, let me just quickly finish it by saying that our approach in this 2023 work is expected to serve as more of a benchmark for future comparison. In particular, I am not aware of large-scale 3D multiple scattering time domain. So this is one of the comparisons you would see both in terms of visualization as well as in terms of errors. So we have done only with 2 obstacles, okay? So the future is going to be, can we do large number of obstacles? And that's where Stewart comes into picture. For example, the one we have done with Stewart has a lot of fast algorithms and memory reduction. Those things are going to be helpful to finish it up. And that's where we started this whole talk is all about. With this, let me close it. Thank you. Hello? Yes. Very good question. In fact, sorry, because of rush, I wasn't slowing down to explain that. Timo, you are absolutely right. For the analysis that we use, we need star-shaped. We need not trapping. Okay. In fact, for the heterogeneous problem, it's a lot more complicated, as you might have seen if you read the paper. What I was trying to say is that we have developed the code, and then we thought, why don't we try to see? I'm not saying coercivity will go through. Let's be clear about this, okay? I am saying that the entire algorithm doesn't seem to fail at all. The formulation, the variational formulation, the sesquilinear formulation doesn't fail at all, including the preconditioners, including the higher order finite element method for the sesquilinear problem. So I'm not claiming that there could be full-fledged coercivity, because you are one of the experts on coercivity, many years ago when you were there. I'm not claiming that at all. All I was saying is that it seems to be a possibility, at least purely from a computational point of view, where all this key inequalities we don't need to apply. It seems to go through. So the point I want to say is that if an industry were to take a one code with analysis restricted to only star-shaped and non-trapping, and then they suddenly come up with a non-star-shaped, do they have to redo this entire thing again because analysis is not there? The point I want to say is that may not be the case. You can use the code even in that case, but proof is in the pudding. Without analysis, it's always a big worry. So that's where I'm saying that I'm not at all climbing. Thank you. Thanks for really highlighting this. Thank you. Hi. Fan Yeah, thank you. Thank you for that. In particular, we have started working on, because the Oscar Bruno's this postdoc work is fantastic. In fact, it was a worry when we were working on it. And then actually, I remember Paul Martin passed Oscar Bruno's paper, and we already working for 2 years on this. It was a real worry. Uh, to be honest with you, we could, as you rightly pointed out, we could take our frequency domain algorithm, plug it in, and especially we have been experts on parallelism, and we have done quite a lot of parallel time domain, whatever, in a different case. That is ideal. To be, if you ask me, that will be the ideal situation. So if I were to compare it, I would compare apples with apples by using similar method. Why this is not comparison with apple to apples is that this is a convolution quadrature based method. It does allow any type of incident wave, as you would know that that there are restrictions in Oscar Bruno's nice paper using the higher order algorithm. There are incident wave issues, yeah. So that's got to be tackled. So they have done some amount of thing, and also this kind of stability that convolution quadratures provide. It's not quite clear yet to me. Those classical method, by the way, at the continuous level, that method is very classical Fourier method. I talked to Paul about this. So this is the question of using the right kind of a frequency domain algorithm. So honestly, Oscars, for that example, especially the wideband signal example I've shown, it beats everybody, including mine, very clearly. In particular, if you have read the paper carefully, I've written very clearly that it is only concerned with only convolution quadrature based algorithms and comparison with that. And there are other types of algorithms for which it's sort of, I didn't write it's a fair comparison. I just am restricted to that. I am going to do this in future. In fact, that's going to be fantastic. And that time, I should be able to compare apples to apples with this work with potentially 2024, 2025. I'm very slow on this. That's what it is. This is a very good question. By the way, thank you to your work with Tom and Leslie. And that was very, very interesting. In fact, thanks for you being the editor to handle this paper. And that is quite a challenge as well to make it work. Thank you. Thank you.